All right, this is section 11.10, video 2. We are continuing with our Taylor and Maclaurin polynomials, Taylor and Maclaurin series. So everything we ran through in the last one was basically a Maclaurin series because everything was centered at 0. So this one, the Taylor polynomial, could be centered anywhere. Doesn't just have to be at 0. The nice thing about this is it's really exactly the same formula. The only difference is this piece right here. Well, technically in this piece right here. It's instead of just being x to a power, it's now x minus the center at a power. We've kind of been doing that already. We just don't typically write the x minus 0 for the Maclaurin polynomial. And when you start to substitute values into your derivative, they are no longer going to be 0. They're going to be something other than 0. It's kind of interesting because I see a lot of questions asked, find the Taylor polynomial centered at 0. Well, that's really just a Maclaurin polynomial, but that's sometimes the way it's worded. Typically, if you ask me, it should say to find the Taylor polynomial centered at 3 or something like that. But sometimes it won't actually use Maclaurin polynomial. So again, this is where I was kind of mentioning, I hope that Taylor didn't invent this whole thing, and then Maclaurin says, well, I'm going to center mine at 0 and call it Maclaurin and make lots of money. Yeah, I'm just jealous because I didn't think of it. Anyway, so a Taylor polynomial, exactly the same thing as what we've been doing. It's still going to be the nth derivative over the n factorial, x minus the center to the nth power. Exactly the same idea. So let's go ahead and just develop one. We'll identify the 4th degree Taylor polynomial for f of x centered at x sub 0 equals 3 pi halves. So there is no actual function here, so the only thing we can do is actually write this out in general. So the first term is always going to be your function evaluated at the center. So our first term is literally f of 3 pi halves. Then we want to add to that our first derivative, so f prime at 3 pi halves over 1 factorial x minus the center, which is 3 pi halves to the first power, plus the second derivative evaluated at 3 pi halves over 2 factorial x minus 3 pi halves, you guessed it, squared. Now, be careful here because this does say identify the 4th degree Taylor polynomial. 4th degree means that the x part has to be raised to the 4th power. It's not how many terms there are, it's the degree of the x. So we've still got a couple more terms to go here. So we need to do the third derivative at the center, 3 pi halves over 3 factorial x minus 3 pi halves cubed. And then our last term will be the 4th derivative at the center, 3 pi halves, all over 4 factorial, x minus the center, 3 pi halves, to the 4th power. That would be a 4th degree Taylor polynomial centered at 3 pi halves. All right, so now let's go ahead and try to develop one of these. So we want to find the Taylor series for f of x equals the natural log of x centered at x equals 2. Okay, this is obviously one you could not center at 0 because the natural log of 0 doesn't exist. So the only thing you could do would be to center it at the natural log of x. And when I talk about centering something, I haven't really given you like a graphical representation of this. Let's say, this is just going to go back a little bit. This is not this problem, but let's say we go back to when we did e to the x. Okay, we know e to the x looks something like that. Not polynomial. But when we center it at 0, which is right here, okay, we know it's going to be convergent at 0 because a power series is always convergent at its center. The more and more terms that we put on this thing, the closer and closer this polynomial is going to be a representation of this function. So let's say we do, I don't know how many terms it would take. Let's say we do 7 terms. Maybe those 7 terms are convergent all the way out to here, and then it starts to split off and do something else. And maybe it's, it's convergent this way down to here, and then it starts to split itself off just a little bit. But within here and here, it's like perfectly convergent. It's exactly the same thing. And the more and more terms you do, the closer and closer the representation is going to be to exactly matching the polynomial. So when we centered at 0, that just means that the center of this thing, the center of your interval of convergence, is at 0. If we center this one at 2, this natural log, this will look a little bit better because this will actually be the natural log, something like that. It just means that we are centering this thing like right there. That's our center. And then we want to write a polynomial that hopefully matches this natural log pretty closely and fits that curve. So that's what we're doing. Okay, so let's go ahead and go back and actually start doing this thing. So we know that to do this, we need a bunch of terms, starting with the original function. Then it's derivatives. We need a bunch of derivatives. So the derivative of natural log of x is 1 over x. Second derivative. So that's x to the negative 1. If you bring the negative 1 out front and reduce the power, you're going to get negative 1 over x squared. Third derivative. That's negative x to the negative 2. So if you bring the negative 2 out to the front, it becomes a positive, and then it'll be over x cubed. So this will be a positive 2 over x cubed. And again, if you start picking up on the pattern here, without actually writing all these derivatives out, what you'll see is the next one is going to be negative 6 over x to the 4th. The fifth derivative will be positive 24 over x to the 5th, and so on. So what you should see is that the signs should be alternating back and forth, and really you're just taking that power and multiplying it by the numerator to get the next numerator. So now we need all of these things evaluated at 2. That's important because it's not centered at 0 anymore. So we need f of 2, which is going to be the natural log of 2. F prime of 2, that's 1/2. F double prime of, not of x, of 2. Negative 1 over, and I'm going to write it this way for right now, 2 squared. It's a double prime. F triple prime of 2. Positive 2 over 2 cubed. And again, there is a reason that I'm writing it like this. Fourth derivative at 2. Negative 6 over 2 to the 4th. Fifth derivative at 2 is 24 over 2 to the 5th power. Okay, the reason for writing it like that is because it's going to be easier for us to start developing this pattern as we go. So let's go ahead and write the first so many terms out. So we've got the natural log of 2 plus first derivative, 1/2 over 1 factorial x minus the center to the 1st power, plus second derivative, negative 1 over 2 squared over 2 factorial x minus 2 squared, plus third derivative, 2 over 2 cubed, 3 factorial x minus 2 cubed. I'll probably just write one more because I'm going to run out of room here. So plus, let's see, fourth derivative, negative 6 over 2 to the 4th power over 4 factorial, x minus 2 to the 4th, so on. All right, so let's see if we can actually figure this pattern out. One thing I noticed is that natural log of 2 kind of stands out like a sore thumb. It doesn't actually fit any of the pattern here. So I can't really use that in the pattern. It's still part of the series, but I can't use it in the pattern. So let's take a look at what everything else is doing. So I'm going to look at a bunch of different parts here. The numerators of the numerator, so these little fractions on top, these numerators are following a pattern. I'm not worried about the positive negatives, although we can see it's going to be alternating. We know we're going to have an alternating term, so let's go ahead and throw that in there. We'll just throw a negative 1 to the n in there right now. Again, whether it's n or n plus 1, we'll figure that out in a second. The numerators, 1, 1, 2, 6, and if you look at the other one, it's 24. Excuse me. That is a very specific pattern. Okay, if you haven't picked up on what that pattern is, that is the pattern for a factorial, right? 0 factorial is defined to be 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. So on the numerator there, what we have is a factorial. So I'm going to write n factorial, which is telling me we have to start this at 0 because I've got that 1, 1, 2 pattern. So we know that our sum, we come down here, it's going to start at 0 to infinity. So let's see, can we fill in that first one there? So to make that right, that's going to have to be n because 0 factorial will give us that positive value. So we're good there. As a matter of fact, I need to shift this just a little bit, sorry. Shift it down just a little here. So that'll be n goes from 0 to infinity, negative 1 to the n. Okay, and I know I'm going to have that n factorial on top. Okay, if you look at the denominator of those little fractions, I'm going to have a 2, 2 squared, 2 cubed, 2 to the 4th, and so on. So really, it's just 2 being raised to another higher power. But that power does not match the factorial. So that's going to be 2, but this has to be technically 2 to the 1st, 2 to the 2nd, 2 to the 3rd, where the numerator really started at 0. So I really need to add 1 to each one of those n's to make it work. So now if I plug in 0, I do get the 0 factorial over 2 to the 1st. If I plug in 1, I get 1 factorial over 2 squared, and so on. In the denominator, so those are going to be 1 factorial, 2 factorial, 3 factorial. So that also looks like it is an n plus 1 factorial. Because again, those don't start at 0, they start at 1 there. And then I've got this x minus 2. Well, those terms also, the exponents also match the factorial, so that's going to be raised to the n plus 1 as well. Okay, we don't want to leave what we've got there in its current form. The x minus 2 to the n plus 1, perfectly fine. But what you should be able to see, I'm going to kind of circle this whole thing right here. We bring this part over here and we write it. That's literally n factorial over 2 to the n plus 1 times the reciprocal of the denominator. Remember that that's like all having it over 1, so it's 1 over n plus 1 factorial. And reducing those factorials, the n factorial and the n plus 1 factorial in the denominator are going to cancel out and leave just an n plus 1 in the denominator. So what that's going to give me after all of that, it's going to give me a 2 to the n plus 1 times n plus 1 in the denominator, and I'm just going to throw that x minus 2 to the n plus 1 on the top. Okay, and that is probably the most simplified form of the power series, centered at 2 for the natural log of x, except kind of forgot that guy right there. It's still part of the series. It is literally part of that series. So in order to write this correctly, I can't leave it off. It's part of the sum, but I can't really put it as a part of the pattern. So what we do with a term like that is literally just say, okay, we'll add it to the front because it didn't really fit the pattern, but it is part of the series. So we have to add that to the rest of the series. So that is the natural log of x centered at x equals 2. Okay, that's probably one of the more complicated ones when you have to develop one like that from scratch. All right, that is developing a Taylor series centered at something other than 0. Down here are probably those 5, like I said, most important Maclaurin series. 1 over 1 minus x we've been dealing with. I hope you kind of already know that one by now. It's x to the n. It's kind of like your baseline. E to the x, not terribly hard to develop if you have to, because the derivatives are all e to the x. Probably still best just to memorize. It's x to the n over n factorial. Sine of x and inverse tangent of x, almost identical, except for that the sine of x has the factorial and the inverse tangent does not. And then the cosine of x, if you already know the sine of x, you probably don't need to memorize because it's just the derivative of sine of x. And you can probably do that pretty quickly and simplify it. One way or the other, you need to know all 5 of those pretty quickly and pretty easily. All right, now let's get into some little bit of tricks here. So we can use, just like we've done in the past, we can use some of the known Taylor or Maclaurin series to find approximations of polynomials. We're going to find the Maclaurin series for e to the negative x squared. Again, definitely not a polynomial. What we're going to do is we're going to start with the known series, the one that we kind of know now, which is e to the x, and we're going to build it based upon that. So this is what we're going to do. E to the x, okay, from the previous page and from what we've done, is the series as n goes from 0 to infinity of x to the n power over n factorial. Just like we did when we were building power series based upon the geometric series, we can do the same thing here. What you should notice is what took the place of the x in e to the x is negative x squared. It's basically kind of like your r. It's not really r, but that's kind of what it's like. So down here, we are going to have e to the, and we'll replace x with negative x squared because that's what took its place over there. So if that's the case, over here, what's going to take the place of the x is negative x squared. Okay, everything else will stay the same. And then we'll simplify because we can distribute that n power throughout the entire numerator, and this is the more common way it's going to look. And also, you'll be able to do more with it after this. So we're going to simplify. So we're going to distribute the n to the negative 1, which is going to give it an alternating term. And then x squared to the n is x to the 2n over n factorial. That is the power series representation for e to the negative x squared. And there was no reason to try and start taking all kinds of derivatives and develop it that way. That would have been a pain because the first derivative, not so bad. The second derivative is going to incorporate product rule, and then after that, it's a bunch of product rules, and it's just a real pain. So use the known series, if you can, to manipulate to get these lesser known series, let's put it that way. Okay, and the reason this works is because this is centered at 0 and it's a Maclaurin series. This does not work so well if it's not a Maclaurin series. All right, example 9 says find the coefficient of the x to the 6th term in the Taylor series expansion about x equals 0, again, really just Maclaurin, where f of x equals sine of x squared. Okay, I don't really want to develop the entire Maclaurin series for sine of x squared. But I already know from what we've done before that the sine of x series is the series from n goes from 0 to infinity, negative 1 to the n power. And this is going to be the odd powers. The sine one is odd. So it'll be x to the 2n plus 1 over 2n plus 1 factorial. But I don't want the series, I don't want the coefficient for sine of x. I want it for sine of x squared. So we are going to replace x with x squared. It's just a substitution. Excuse me. So this will be sine of x squared now, which means in my series, I'm going to replace x with x squared. So we'll have an x squared now raised to the 2n plus 1 over 2n plus 1 factorial. And we want the coefficient of the x to the 6th term, which means what am I going to plug in to n to get x to the 6th? Well, if you really want to simplify it, this is x squared to the 2n plus 1 power. What would you have to plug into n so that ultimately you end up with an x to the 6th? And the answer to that is n equals 1. If I plug in n equals 1 in here, that's going to give me a third power on the outside. X squared to the third is x to the 6th. So really what I want to do is I want to say, okay, when n equals 1, this is going to give me my c sub 6, or coefficient of the 6th power term. So if I plug in n equals 1, that's going to be a negative, because that's going to be from here, that's going to be a negative power. Plugging in 1 there gives me x to the 6th on the top. Plugging in 1 into the denominator is going to be 3 factorial, which itself is 6. So if I rewrite that, that is negative 1/6 x to the 6th, meaning that the c sub 6 is negative 1/6. So there's the coefficient of the x to the 6th term in the Taylor polynomial expansion for sine of x squared. And notice we did not have to go through and do the entire Taylor polynomial expansion by doing all the derivatives and stuff. It's much easier if we can manipulate a known Maclaurin or Taylor polynomial at this point. All right. Find the Maclaurin series for cosine of x. We've already done that, so I don't really have to find it. We're just going to write it down. Again, you can either take the derivative of the sine function, or you can just memorize this one. This is the even-powered one, so it is x to the 2n over 2n factorial. Okay, done. Nothing for us to do there. I don't really want you to work that one out again. But now we're going to use that and find the Maclaurin series for x cosine of x. So again, we start off with the fact we know cosine of x, and we just wrote it down. X to the 2n over 2n factorial. The difference here is I'm not substituting anything in. I'm actually multiplying the entire cosine by x. It's okay to do this because remember that when you create a series, you're creating a polynomial. I am multiplying cosine of x's polynomial times another polynomial x. When you multiply polynomials, you literally just multiply the terms together. So all I need to do is multiply this series by x, which means that what we get is the series from n equals 0 to infinity, negative 1 to the n. So now if I multiply that x on top, excuse me, the x to the 2n on top by x, we get x to the 2n plus 1 over 2n factorial. That is the series for x cosine of x. And again, the biggest difference here is this is a polynomial. So when I multiply that polynomial times one of these series, which is creating a polynomial, it's okay, you just multiply the x terms together. That is not going to be the case for the next couple of examples that we have. These next couple ones actually take a bit of time, so I think we've got, what, 4 examples left to go. I'm going to come back with a third video, and that should finish us off.